Hello everyone. Thank you very much for joining this event. I am Diana Radulescu from Processes. So today we will have our webinar on the topic corrosion process of metals, mechanism and protection methods. To start with, I would like just a second. I would like to go and present you a little information related to MDPI. As you may already know, we are a pioneer in scholarly open access publishing, and we support academic communities since 1996. We are based in Basel, Switzerland, and MDPI has the mission to foster open scientific exchange in all forms across all disciplines. We have more than 480 diverse and open access journals, including 473 peer-reviewed journals and 9 conferences journals, which are supported by more than 295,000 academic experts who share our mission, values, and commitment to providing high-quality service for authors. About our journal, as some of you may already know, we are an international peer-reviewed open access journal on processes, systems in chemistry, biology, materials, energy, environment, and many other subjects. Right now, as you can see, our current impact factor is 5.5, while our impact factor right now is 2.8. So if you would like to find more information, you can check our website. As for the topics related to our journal, you can see here our sections. So as I mentioned before, we have sections from chemical processes to energy systems, catalysis, enhanced processes, pharmaceutical processes, up to AI-enabled process engineering. For today's schedule, as you may already see, our chair will have 10 minutes to start the webinar, and after that he will give the microphone to our colleagues and after all the presentations that are finished, we will have a Q&A session. So if you want, you can leave your questions on the chat or the Q&A box. At the same time, after that, Professor Jesus will be closing the webinar. So here are relevant special issues for this event. The special issue corrosion processes of metals, mechanisms and protection methods, which is edited by Professor Jesus and Professor Enrique Vera Lopez. The deadline for submission for the special issue is until the end of November 2025. As I mentioned, if you have some questions, you can leave them in the QA box and we will help and reply to them timely. To start with, here's our first speaker, Dr. Genevieve Mendez Figueroa. After that, we will move on with Professor Fabiola Pineda. And after that, as you can see here, the information of our chair. So I will give him the hand and to start this event. Okay. Professor Jesus, if you would like to give a few words for this event. If not, we can move on to Dr. Genevieve.
Well, first I wish to give a thanks to everybody to be here. I know that the difference between the schedules is very, very hard for some people. And thanks to the Dr. Henry, thanks to Dr. Pineda to attend the invitation. And thanks to the attendance, because it's very important for us that the attendance to promote topics that are interesting for the attendance. It's all for me. I think Dr. Henry can begin with her presentation.
Well, good morning, everyone, or good afternoon, depending on where you are. thank you for being here. I'd like to start by thanking the organizers for giving me the opportunity for this, some of the results of my work. And of course, thank you all for attending and for your presence and interest. Okay, so today I'm going to share part of my research for the research we've been working on regarding advanced protective coatings, in particular, how we can improve corrosion resistance in harsh environments using smart self-healing technologies. So first, I'll walk you through the challenges of cathodic disbondment, how we address them by incorporating functional microcontainers into an epoxy coating, and the electrochemical results that we obtain. Okay, so corrosion protection methods are usually selected based on a specific application. However, in many real-world problems, in many real-world systems, such as submerged pipelines or chip holes, it is often necessary to combine multiple strategies to ensure long-term protection. In these systems, coatings serve as the first line of defense, acting as a physical barrier that prevents direct contact between the metal and the environment. Some coatings are enhanced with pigments that act as corrosion inhibitor, offering localized protection, and additionally, cathodic protection systems provide a second layer of defense, further delaying coating failure and extending service life. One of the most widely used coatings in the industry is fusion bonded epoxy, or FBE, due to its excellent adhesion and anti-corrosion performance. However, FBE is highly susceptible to a phenomenon called cathodic disbondment. This occurs when the cathodic protection current generates a highly alkaline environment at the metal and coating interface, degrading the chemical bonds in the coating, especially at the defects or scratches in the coating, and causing it to lose adhesion over time. Industrial cathodic protection systems typically operate between minus 0.85 and minus 1.2 volts versus the copper sulfate copper electrode. And yet, even at minus 1.2 volts, coating detachment can still occur. From the coating so this is an issue, no? From the coating perspective, this issue can be tackled through strategies like improving adhesion, enhancing barrier properties, or incorporating active or self-healing functionalities to mitigate local damage. In this work, I focus on the self-healing coatings, specifically those designed to release active compounds that can protect exposed metal areas. And this is usually done by embedding micro or nanocapsules into the coating matrix. Well, the choice of container materials is crucial. Silica, for example, has chemical compatibility with the epoxy matrix, and also has a high loading capacity, which is determined by a specific surface area. However, silica doesn't actively protect the metal. So, as a purpose, the zinc-based materials can offer multi-functionality. Zinc oxide not only acts as a sacrificial pigment and forms a stable passivating layer, but as a semiconductor, it can also delay electrochemical reaction at the at the metal surface. Okay. So here there are some values that we can obtain with different methods of synthesis for zinc oxide. In addition, tannins extracted from sources like the Mimosa tenuiflora bark, which is this tree. These tannins can act as thrust converters by forming protective complexes with iron ions. So that's why we selected this for loading our container. And then for an effective release, the containers must respond to a trigger. In this case, we selected a pH-sensitive system because cathodic despondent produces an alkaline environment. So we selected the iron tannic acid complex for its ability to deprotonate and release the inhibitor under high pH conditions. So this work was motivated by the need to develop smart coatings that can respond to early signs of failure, and our approach involved incorporating microcontainers into an epoxy matrix. These microcontainers are based on zinc oxide, which provides an active protection, and also they are loaded with corrosion inhibitors such as tannins, which act as thrust converters. And our goal is to improve the resistance to cathodic despondent by enabling a controlled release of these inhibitors triggered by changes in pH and the metal coating index. Okay, so the methodology first started by the synthesis and characterization of zinc oxide based microcontainers. And then we added in different concentrations to the epoxy matrix. And then we evaluated the electrochemical impedance spectroscopy during 28 days. And after that, we made a cathodic despondent test. So first here, it is the synthesis method for the microcontainers. In the first step, the extraction of the Mimosa tenuiflora bark active substances was done with using ethanol. Okay. Then the synthesis of zinc oxide was made with the hydrothermal synthesis, where we control the temperature and pressure to obtain mesoporous structure. And then we combine these two materials into ethanol solution. And after that, we add a final layer made of the iron tannic acid complex. So at the end, we have our micro container was in the core, zinc oxide. It was loaded with the Mimosa tenuiflora bark extract. And finally, we got the external layer that it was pH responsive. The characterization techniques that we use for the containers, for the microcontainers, we use the nuclear magnetic resonance, BET method, scanning electron microscopy, thermal analysis, and including in this, we conducted the thermal gravimetric analysis. In the cathodic despondent test, we got this configuration where we have the sample in the bottom and we attach as an acrylic cell. And well, one of the important aspects in this test is that we need to we need to make a holiday in the sample so we can accelerate the reactions, the electrochemical reactions there in the holiday. So this is a configuration of the cathodic disbandment test, and it was conducted under minus 1.1 volts versus the silver chloride. These tests were made after 28 days, and after that we evaluated the disbanded area. Then for the electrochemical impedance spectroscopy, we use these conditions. And we evaluated in the range of frequency between 10 kilohertz and 1 kilohertz, where we could be able to detect the electrolyte resistance, the dielectric properties of the coating, and charging and discharging processes at the electrocoating. All right. So in the results, here. As we can see in this slide, an effect or, sorry, that's the CEM image revealed that the zinc oxide microcontainers had a hierarchical spherical structure made of nanosheets. Then with the bed analysis, we confirmed mesoporosity and a specific surface area about 13 square meters per gram, which is lower than expected, but with sufficient voids to store around 40% of the inhibitor, as the thermogravimetric analysis showed. Then the EDS analysis showed carbon oxygen ratio consistent with tannin presence. And then with the nuclear magnetic resonance, we confirmed the presence of condensed tannins in the mimosa tinifera bark. Okay. Then the microcontainers were added at several the concentrations of 0.5, 1, and 2%. And in the cathodic disbandment results showed a clear trend where the higher the concentration here, the smaller the disbanded area. And similarly, the current required to maintain minus 1.1 volts in the sample decreased as the concentration of microcontainer increased. And this is likely due to the zinc oxide semiconductor's nature, semiconducting nature, which helps store charge and form a passive layer. Now, and the EIS analysis showed that a single time constant governed the system, regardless the presence of the microcontainers. And which is interesting here is that when we added the microcontainers, we can see that in the phase angle, the behavior is more stable when the concentration is higher. So here at 2%, we can see a maximum peak in the phase angle of minus 75 degrees, indicating that the barrier performance is better when we added 2% of the microcontainers. And then we simulate, or we fit the data using an equivalent circuit with a one single time constant, where we use the air resistance to simulate the solution resistance, and then a parallel configuration of a constant phase element with a resistance to represent the charge transfer resistance and the double layer capacity. Yes, so the values that we calculated here were this. In the first image, we have the charge transfer resistance, and in the second one, we calculated the double layer capacitance using the Buck equation. And yes, well, the results here, which is interesting, is that when we added 1%, the charge transfer resistance present a drop, which indicates that the system has can have an agglomeration, and that can create paths that can affect the performance of the coating. So after that, we can see that adding 2%, this resistance increases, which can be indicative that the structure can be more compact, forming a dense basic layer that enhances the protection. And in the capacitance, we can see lower values when we added the microcontainers, indicating that a more protective layer is presented with the addition of the microcontainers. Now, if we analyze the pH of the bulk, and initially we can see an increase of the pH due to the generation of OH ions, and because of the tannins release that also has OH in their structure. And however, at higher concentrations, a pH drop was observed, and this is likely due to the formation of iron tannic complexes, which release hydrogen ions, as we can see in this chemical reaction. And moreover, zinc oxide electron charge capacity may suppress the catalytic reaction at high concentration, resulting in slower and more controlled release to the inhibitor. So to conclude, incorporating zinc oxide and tannin microcontainers into an epoxy coating significantly reduces the cathodic disbondment and current demand, particularly at high concentrations. And this suggests a dual function mechanisms where zinc oxide offers a passive protection and modifies the local chemistry, while tannins provide an active inhibition. These results point to a promising strategies for designing smart coatings with controlled inhibitor release, though further investigations such as local pH mapping or release kinetics is needed to fully understand the underlying mechanisms. And well, these are some references. And that's it. Thank you very much.
Thanks. Thanks, Henry. Well, you have one question. I don't know if you answer the question in the, or you can see the question in the section question and answers, Henry.
Yes, here I can see one question. It says, in cathodic disbondment test, what is the significance of minus 1.1 volts versus the silver chloride potential? Okay. Well, in the cathodic disbondment test, we try to accelerate the cathodic reactions. The cathodic reactions in the like here, yes. So to accelerate these reactions, we polarize under -1.1 volt. And here the reactions that happen or that occur is the evolution of hydrogen and um, um, yes, and how do you say this? The hydrolysis of water. Yes. So from one side we um, induce the OH ions, and on the other side we accelerate the hydrogen um, molecule formation. So this is why we use -1.1, because we accelerate these reactions that happen when we protect using a cathodic protection system.
Well, thanks, Genevieve, for your representation. Well, the next presentation in the schedule is mine. Well, let me share the presentation is the electrochemical characterization of hydrophobic lithium dioxide nanoparticle coating applied by spray on aluminum 7075. As a brief introduction, uh, the efficiency of the inhibitor depends on the stability of the former shell and inhibitor molecules. Most of the inhibitors are absorbed into the metal and displace the water molecules on the surface and forming a pressure barrier. When we apply a super hydrophobic, we are looking to make a self-cleaning system when you can when the drop water of the drop of electrolyte can be displacement to another part to reduce the corrosion. For that reason, we are applying this type of super inhibitor. The alloy, the aluminum is employed because it's a very used in aeronautical and automotive industry. To realize the super inhibitor, we use the strober method, and we employ 10 milliliters of the oxide silicium particles mixing a 99 milliliters of isopropyl alcohol and 300 RPM. Um, in this, in the this figure shows how we take the picture of the drop to define that is an super hydrophobic. For electrochemical characterization, we employed two techniques. The two techniques that we employed are the electrochemical noise and potentiodynamic polarization. In the potentiodynamic polarization, they were realizing on sodium chloride and sulfuric acid. The electrochemical noise were realized in 3 electrode cells with two nominal identical electrodes due to the standard ASTM G199, and the technique of potentiodynamic polarization was performed with 3 electrodes, but we did not use nominal identical electrodes. We employed a cell as this one with a counter electrode. The data was 1 data per second, around 2048 data. The importance of electrochemical noise is because it's usual that in this kind of system we present a localized corrosion. when we have a localized corrosion, we can the use of potential dynamic polarization or also techniques can present some limitations because they are using to measure or to determine corrosion of uniform systems. But when you have localized corrosion, when you have a this system, the electrochemical noise is a best option because it's a technique that measure the localized corrosion. Well, our results. The first results are the same obtained before corrosion test. In figure, the A and the B are the aluminum before applying the coatings, and C and D are the aluminum after coating applying. When the coating is applying, you can observe that the coating presents some cracks. Is homogeneous? Yes, it is homogeneous, but it presents some cracks. That cracks can be a problem in the future. The water droplets on a glass substrate look of this way. The figure shows that this is a separator for. Well, our results in potentiodynamic polarization. Potentiodynamic polarization shows how A is for sodium chloride and B is for sulfuric acid. It can be observed how in both media, both electrolytes, the inhibitor application reduce the corrosion kinetic because we have um, a lower current demand. Also, something important is that the hysteresis in sodium chloride is positive, indicating that we have a localized corrosion system, and in sulfuric acid is negative, indicating that we have a uniform corrosion system. So we have two different types of corrosion. And another important thing is that the application of the inhibitor uh, increase the curve, so the potential is more noble, and that means that it's necessary more energy to begin the anodic process. Also, in sodium chloride, we don't have a passivation system, so the system is completely active. For that reason, the, the sample don't present a passivation. In sulfuric acid, the passivation, well, we don't have a passivation, but the system is completely different. In electrochemical noise, we have the signal with the transients. This is for sodium chloride. In the sodium chloride, in the current, we have a large transients indicating that localized corrosion is occurring. On the other hand, in the sulfuric acid, we present a system with transients, but the transients are more periodically. So this indicates that the localization of the tags occur a more homogeneous way. Other way to analyze this is with noise impedance. The noise impedance is very important because they give the resistance to corrosion. For these samples, the resistance to corrosion looks a some very particular behavior. In sodium chloride, the resistance is very similar, but in sulfuric acid is different, and we can look how the aluminum without inhibitor present a higher noise impedance than is in this table. This occurs due to a phenomenon due to the passivation phenomenon, because as aluminum is in sulfuric acid, it tends to generate some oxide layer, and the oxide layer in electrochemical noise, you are measuring the first layer is now as impedance, is now potential dynamic polarization. It's a sensitive test. But in chloridium, in sodium chloride, the aluminum with inhibitor present a higher corrosion resistance in comparison with the aluminum without inhibitor. However, in the last technique, in the analysis, in the visual analysis, we can see very well the behavior of pitting. For that reason, we employed uh, analysis by recurrent plots and Hilbert spectra, comparing with the micrography. This is the sample without coating, without coating, exposed to sodium chloride. In the figure, you can see that a non-homogeneous or an heterogeneous oxide was generated in these zones. It can be observed in this figure because we have energy at low frequencies. It indicates that a localized corrosion is occurring. In this part, the recurrent plot shows how these lines, how a localized corrosion occurs. So the system that is occurring in this media is localized. On the other hand, when we have the sample coating, it is very interesting, this one, because the micrography and the technique shows how the localized corrosion is occurring, because we have attacks in this part, and in this part that is in the cracking zones of the sample that I mentioned at the beginning of the presentation. And in the Hilbert spectra, we have energy accumulation at high frequencies. When you have energy accumulation at high frequencies, it indicates a localized corrosion system. You have a low frequencies, it's an homogeneous corrosion system. And your current plot show how we have at beginning an accumulation of attacks. That is normal in the system because we have the equilibrium of the system. But after one time, we have attack in this part that is around 1,100 seconds. Is around this one. The majority is this one. When we study the system in the of the of the sulfuric acid on sulfuric acid, the sample doesn't present something in particular. So the high energy is accumulated on low frequencies. I think indicates that an homogeneous attack is occurring. However, when we employ the system, you can see the difference between an homogeneous attack from a localized attack. You have a homogeneous attack, your current plots is or should be look like this one, with a distribution, homogeneous distribution of lines, or way to say. However, in the micrography, you can see how the content is still in some areas, and that means, well, in the next, in this, that means that the corrosion behavior or the corrosion system is the same. What is the difference? The aggressivity of the electrolyte. Mm, Chloride ions begins subtaxing the crack zones and generates a dissolution of that zones. However, in the sulfuric acid, the behavior is the same, but as sulfur is a more aggressive media, the dissolution of the inhibitor is biggest. Well, as conclusion, the superhydrophobic presents a hierarchical structure. However, the distribution was not completely homogeneous. It usually the crackstones. The sodium chloride electrolytes generates a little oxide layer, but the oxide layer is weak to the presence of the chlorides, and it avoids a homogeneous passive layer barrier. The corrosion mechanism of superhydrophobics consists in attacking cracked zones, dissolving the material, and coating present a higher corrosion resistance in sodium chloride than in sulfuric acid. And it's important to study the behavior of noise impedance because it means it reflects the evolution of the corrosion resistance. But one of the most important, I think the most important is this one. Corrosion tank coating concerns a mixed corrosion that occur first as localized attacks in some zones to after some time this localized attack dissolve the entire material of the entire coating, generating a uniform corrosion. For that reason, it can present some variations. Well, this is everything by me. Thanks for your attention. Well, I can see if somebody have any question, or thanks for all your attention. The next presentation is for the Dr. Pineda. I don't know if you can compare your presentation, please.
Yes, of course. Just give me 1 second, please. Well, I will start. My name is Fabiola Pineda. I'm from Chile, and I always like to start with a little bit of context because I think that the question is, where is Chile? Well, I work in Universidad Mayor, which is in Santiago, the capital of Chile. Here is Chile. In the very south of Latin America, we are the longest country in the world. We are in the south, and it's very important to say that because Chile is this country, and if you see this image, we have a pink color, which means that we have a lot of sun. Pink is related with the highest level of direct normal irradiation, which means we have the highest level of sunlight in the world. And we can use sunlight to produce electricity through the concentrated solar power technology. This is a picture of the Cerro Dominador plant that is already operating in Chile. It's in the Atacama Desert, and I draw in here another 3 suns because there are another 3 plants under construction. In these plants, we have 3 different generations, Gen 1, 2, and 3. The difference is that in generation 2 and 3, we will use a tower to focus the sunlight and to produce electricity. This is the one that is already in Chile. We have a solar field, a tower, and 2 big tanks. Inside the tanks, there is a molten salt. So we have 4 different plants. They have different power. All of them has a tower. They have different storage capacity, and they use molten salts. And what is a molten salt? It's a phase change material that is used in this type of applications, and it is used to store solar energy. Normally, in this type of application, it is used a binary mixture of nitrates called solar salt. This is how the mixture looks like, and this is produced also in Chile. This is a big picture of this CSP plant. It's the only one in Latin America. And in here we have some pipes. This is the tower. We have some metallic pipes, metallic bulbs, and metallic storage tanks. Inside of tanks, we have a molten salt, which is 100% ionic. So in the beginning, the tanks look like this, but with the pass of time, they look like this. They corroded. And this is a big problem we have because in these plants, we have some fractures related to corrosion. And we cannot do any measurements on the plants, so we have to simulate these conditions on the laboratory through some gravimetric or electrochemical setup. I think that most of you knows about this. In our case, we use molten salts in the laboratory, and we use the same stainless steel that is used in the CSP plant. And in the case of gravimetric setup, we have some advantages, some disadvantages, and the same with electrochemical setup. We have worked with both of these setups. With gravimetry, we have studied different alloys that can be used in this type of applications, different types of thermal treatments to avoid some problems related to corrosion and to welded joints. We have also studied different corrosion mechanisms, for example, flow accelerated corrosion in molten salts and another types of metallic alloys and different type of molten salt mixtures. But we have also carried out some electrochemical setup. We have used electrochemical impedance spectroscopy to study some experimental alloys and experimental molten salt mixtures and some commercial alloys and commercial molten salt mixtures. But this is not the end for CSP plants because there is a project called Sunshot that is looking for reduce the cost of this type of technology, and this can be reached developing new molten salt mixtures. So one idea is to use chloride molten salts, and maybe this is going to produce a question in all of you because chloride is really corrosive. Other alternative is carbonate mixture of molten salts. And the third alternative is nanofluids. The one that is more promising is nanofluids, and nanofluids are a colloidal suspension of initially nanoparticles that are dispersed in a liquid medium, or in this case, a molten salts. So this is a picture or an image of different types of nanomaterials. There is a lot of information about nanoparticles in the thermal properties, physical properties of molten salts, and about corrosivity. This is very interesting because the addition of nanomaterials can reduce corrosivity in this type of applications. But there is a problem about nanoparticles, and this is they can agglomerate and they are not stable in the time. So we are moving to another type of nanomaterials. Now we are studying 2D nanomaterials, these ones, and particularly two types, HBN and MXenes. And MXenes are a new type of family of nanomaterials, really popular these days. They were discovered in 2010, and they can be used in different applications, not only in energy, but I will focus on energy storage. And what we do with MXenes? Well, we can add MXenes to molten salts to the electrolyte, or we can use MXenes to produce coatings. When we add MXenes to the media, they can act as corrosion inhibitors. And when we produce some MXenes coatings, they can act as chemical barrier, preventing the contact between the metallic alloy and molten salts. So we are now doing some experimental and theoretical studies related to these theories. And I can show you a little bit of this information because we are now producing some manuscripts. In regards to the inhibition effects, we have two theories. The first one is related to the use of this type of nanomaterials that they fill the pores of the different corrosion layers and avoid the corrosion degradation of the metallic materials used in these applications. This is the case when we don't use MXenes, and this is the case when we use MXenes. As you can see, we have defects in this case, we have internal corrosion damage, but when we use MXenes, we don't have that problems. We also believe that related to the inhibitor effect, we have a second theory that is related to the competitive absorption of corrosion species, of corrosion ions with MXenes, and they can modify the redox equilibrium. We are doing this with some MD simulation. So we will share in the future these results. And about the barrier effect, we have two theories again. Well, the vaccines can act as a physical barrier and block some electronics reaction so we can avoid corrosion. This image can represent that. In the other theory related to barrier effects is that vaccines coatings can seal himself and avoid corrosion on time. So we have very good results, very promising results about this. And we have published some of this this year. This paper is related to the thermal and physical properties of molten salts. This is how we can do some changes in the surface of different substrates to enhance the adhesion of coating vaccines. And this is one of a study which is not under extreme condition, but that's proof that vaccines coatings can be really, really good to avoid corrosion. So to conclude, we can say that molten salt corrosion is a lifetime limiting factor, that we can use gravimetric and electrochemical impedance setups to study these type of problems, that we are now studying nitrates, which is very good compared with other strategies like chloride and carbonates, and that vaccines are very promising as additive and as barrier coatings to avoid corrosion. We have some outlooks, like standardize some protocols to prove what happened in chlorides, what happened with vapor, what happened with different treatments to produce the vaccines coatings, and to analyze how the vaccines are distributed in the corrosion coating. And to finish my presentation, I would like to say thank you to my work, to some collaborators, and to the National Agency of Research, and of course to all of you for hearing my presentation. So thank you very much.
Thanks, Dr. Fabiola, for your presentation. It's a very interesting topic. Well,
Thank you.
well, the next thing, well, we don't have the next in the schedule. Well, I don't know if we have any questions.
I also see there are no questions on the chat box. So if there are no questions, I think we can conclude today. So Professor Jesus, if you have some final words.
Well, the final words. Thanks to everybody to be here. Thanks to Genevieve, it's very early in Mexico today. Also, it's very early in the part of Mexico than I am. And thanks to the Dr. Pineda to your presentation. It's a very interesting topic. It's a very nice presentation. And thanks to all the attendants. Thanks to you, Diana, to all the for your following all this process. And well, I don't have anything else. Well, we have right now the special issue of corrosion mechanisms and processes. It can be an invitation to everybody to make the deportation to this special issue. We are waiting for more for your papers. You can contribute in a review paper in an original paper, and we have also we have some discounts, and if you need some discount, you can send an email to me. You in the page of the special issue, they have my email. You can send an email if you have any question, and I will answer you. I don't have any more to add. So thanks to everybody.
Great. Thank you everyone for attending today. This was a really productive topic. Okay. Do we have one question? No. We had a really productive meeting today, so I am really thankful for all the attendees and also our speakers. And for more information, you can also access our website related to the webinar and also of the special issue. I have left some information related to certificates, and I think we can conclude the meeting for today.
Thank you very much. Bye.
Goodbye.
Have a nice day. Bye bye.